everyone. Welcome to the MOFspace webinar series. Today we are hosting our fifth webinar, and I'm very happy that you are joining us. So I would like to remind you that this webinar series is an initiative of EU for MOFs Cost Action, which aim to bring together all experts and researchers who are working in the field of metal organic frameworks. And if you missed any of our webinars, you can easily find them on our YouTube channel and watch the recording at any time. So today we have very interesting and useful webinar. We will speak about structural characterization of MOFs. As you know, sometimes it could be very challenging. But from another side, understanding the structure of the framework is very important because it directly affects how the material performs. So in this webinar, we will see how advanced diffraction methods help difficult to study using traditional techniques. Okay, and now it's my pleasure to introduce our speakers from Rigaku company. So today, together with us, Dr. Maciej Grzywa, Diffraction at Rigaku.
Okay.
Sorry, something happened. Yes, I'm back. Sorry. So he received his PhD in chemistry in Jagiellonian University and has authored or co-authored more than 60 scientific publications. He also completed postdoctoral research at the University of Augsburg, Ulm University, and the Polish Academy of Sciences, focusing on the synthesis and structural characterization of MOFs and peroxide compounds for application in catalysis, gas sorption, and separation. And our second speaker, Dr. Jakub Wojciechowski. He is a senior application specialist at Rigaku, specializing in single crystal X-ray diffraction and electron diffraction for small molecules, supramolecular systems, macromolecules, and high throughput workflows. Since joining Rigaku in 2018, he has supported customers worldwide in optimizing analytical strategies and advancing modern crystallographical techniques. Previously, he served as an academic teacher and crystallographer at Lodz University of Technology, conducting research in analytical chemistry and quantum crystallography. He has authored over 40 scientific publications with expertise in absolute structure determination, charge density studies, and complex molecular characterization. So thank you for being with us today. And now I will hand over the floor to you, please. The floor is yours.
Thank you. Yeah, thank you very much for the kind introduction. Hello, everyone. It's a pleasure to be here. Before starting talking about application of XRD in MOF research, let me quickly introduce Rigaku company. Rigaku is a global leader in analytical X-ray solutions with the focus on the main technologies like XRD, XRF, single crystal, CT, XRT, SAX. Rigaku produces high-quality analytical X-ray instruments and works closely with research institutes and industrial partners. Rigaku products are known for strong Japanese craftsmanship. The company was founded in 1951 in Tokyo, in Japan. This year, we are celebrating 75th company's anniversary. Today, Rigaku has 2,200 employees, is listed on the Tokyo Stock Exchange, and Rigaku has a global presence in more than 130 countries. The headquarters of Rigaku is located in Japan, in Tokyo, where we have also in Japan factories in Hajima, Yamanashi, Osaka, as well around the world. We have many offices as well, factory, for example, in Poland for single crystal diffractometers. Rigaku Europe SE is Rigaku headquarters for EMEA region. We are responsible here for XRD, XRF, XRT, CT, and single crystal. Our office is in Neu-Isenburg, near to Frankfurt and near to Frankfurt Airport. We have 8 demo labs here and 16 application scientists support sales activities. Overall team consists of more than 100 people here. We are very proud of our achievement. In the last 10 years, we have sold and installed about 2,000 instruments in the EMEA region. Selected product portfolio of Rigaku Europe includes instruments for X-ray diffraction, wavelength dispersive X-ray fluorescence, X-ray computer tomography, single crystal and electron diffraction, X-ray topography imaging, semiconductor metrology, and also products for thermal analysis. In this webinar, we will focus on the instruments for XRD, single crystal, and also electron diffraction. As you know, X-ray diffraction is a very powerful tool for characterization of materials. In MOF research, XRD is used in the R&D, for example, for structure determination of the new MOFs, phase identification and purity check, for crystallinity assessment, in the characterization of the metal organic firmware, powder XRD used for example, for phase analysis, as well also for structure solution based on single crystal data, electron diffraction data, as well based on powder diffraction data. There are also XRD diffraction is used for studies for in situ operando, for dynamic studies. In the production and scale up for batch consistency verification, quality control, monitoring post-synthetic modifications, and in the application development, for example, is used for gas absorption, induced structural changes, for example, investigation of briefing MOFs, catalytic site stability analysis, drug delivery, as well is used for investigation of MOF dispersion in membranes. Triazole-based coordination compounds have been studied since the early 80s. Several isostructural compounds have been reported. These compounds crystallize in cubic crystal system within the space group FD3'M. In contrast to the isostructural compounds, copper triazolate, which contains Jahn-Teller active copper-2 centers, crystallizes in tetragonal crystal system. This compound shows reversible phase transition at higher temperature. The synthesis of the copper triazolate was performed under solvothermal conditions, and the reaction time was 48 hours, which results in single crystals with the maximum size of 40 micrometer, which are enabled to be measured by using single crystal diffractometer. To accelerate the reaction, another microwave synthesis reaction was developed that the reaction time was shortened to 10 minutes, resulting always with the product very fine precipitate. This raised the question It is possible to collect the powder data and solve the structure using the data which were collected on the benchtop XRD instrument. And here I'd like to introduce the Miniflex 600 advanced benchtop X-ray diffractometer. The first version of this instrument was for the first time introduced by Rigaku as a benchtop system in 1973. Miniflex has classical goniometer with high angular accuracy and high reliability with the goniometer radius 150 millimeter. Internal and external chiller is here. The system has low weight, maximum 90 kilograms. The system has high power and is possible to use different wavelengths. It's the option to use variable and fixed slits. Miniflex is equipped with a standard X-ray rotating shutter. And also we can install here two types of detectors. 1D detector detects Ultra 2 and 2D XPA 200 ER detector with the excellent energy resolution. Miniflex can be also equipped with different types of attachments, like, for example, sample changer, bulk sample holder, sample spinner, capillary, or also heating stages where we can heat the sample up to a maximum 500 degrees. Different types of holders made from aluminum, from glass, from silicon, so-called low background sample holders can be used. When we check the shape for sample changer as well rectangular for single position, it's also possible to perform the measurement in reflection and transmission geometry, and are also available the airtight sample holders, especially for the samples that are air sensitive. Ab initio structure determination from powder data. In this case, we use the Miniflex, and the data were collected only within 22 minutes in the range of 5 to 100 degree 2 theta. On the right-hand side, you can see the typical structure determination maze, where after data collection, the next step is indexing of the powder pattern, space group determination, intensity extraction, treatment of peak overlap, getting the structure completion, and Rietveld refinement as the last step of the whole process of structure solution. All the steps can be performed in the software, which is called SmartLab Studio 2. This is all-in-one fully integrated software platform from measurement to analysis, which consists of several plugins. XRD measurement plugin we use for to control the instrument as well to start the data collection. And for the analysis, we use, for example, Powder XRD plugin, where on the left-hand side, we can select the task, structure determination, and according to the flow, we can perform all the steps during the structure solution. On the right-hand side, for example, you can also specify a method which you want to use for data analysis. And in our case, indexing of the powder pattern was performed in SmartLab Studio 2. The software suggested different results in tetragonal crystal system with the highest figure of merit 85, and this solution was selected for further steps of structure solution. After that, the space group was determined based on the intensity analysis, and in the next step, powder pattern was decomposed based on the polling method, achieving RWP below 5%. Initial crystal structure model was obtained by applying charge clipping method, and the last step was Rietveld refinement. Refined parameters were scale factors, factor unit cell parameters, profile, background, atomic coordinates, as well displacement parameters. The structure shows two-dimensional channels in B and C direction, and the surface area was 440 square meter per gram.
Okay, so Maciej showed us how to solve the structure using powder data, but in reality, the gold standard is the single crystal or crystallographic approach. And Rigaku in his portfolio has a platform called Synergy. It's named this way because it was developed after merger of Oxford Diffraction and Rigaku around 10 years ago last year. So we also have nice round anniversary. And it took all the strong part from Rigaku and all the strong part from Oxford Diffraction, creating this synergistic platform. So we do have best optics from Rigaku, the best detector, also high peaks, the same that we're using on the powder system, and the best automation. We use Chrysalis Pro, which is the most comprehensive software package, which I will show you in a second. And we have an excellent possibility to measure data. And I want to show you first, before I show you other examples, that it is also possible to measure powder data using single crystal instrument. This is example measurements. It took me slightly longer, so around an hour to measure the same powder that Maciej show you from the Miniflex benchtop instruments. The data is similar, comparable in a quality, allow you also to use normal SmartLab Studio workflow to solve the structure for powder. But the biggest advantages of this one, that this is micro powder diffraction. So normally for the benchtop instruments, you would expect to have a large amount of the sample, when for the single crystal instruments, you can work with very small amount of the sample. But in lots of cases, this is not really required because you can kind of shorten this base that Maciej was tell you about, how to solve the structure for powder using automated structure determination plugin, which is called What Is This? And basically, with the development of the single crystal instruments, when we have a super bright microfocus sources, you can go with the size of the crystals in a 10 of microns, not several hundreds. That's very often people think it's possible. And the crystals don't have to be a perfect one domain single crystal. We easily and routinely measure multi-domain up to 8 domains or even more. And also this is example when I just measure a cluster of the powder, basically. So you can see I mounted on the loop. So this yellow thing is 100 microns, as indicated on this loop. And I took a small amount of material and performed what is called What Is This experiment. It took me an hour to measure it, but it was enough to get the crystal structure solution from it, which you can then use to bootstrap your width refinement on the powder. So what is it, or as we call it sometimes width, is a tool built in directly in Chrysalis Pro. On the right side, you have a small demonstration in video how quick it can be. So you can see there's a crystal rotating on the goniometer, and you will see that it can take basically less than 1 minute to get the structure. This is organic material, but if your MOF crystal diffracts it also well, it will be as fast as this. So there is a publication reference on the bottom, but basically it's just data set that goes for the completeness 50%, and the target is 1 angstrom. And that's a requirement that to solve the structure with direct or intrinsic phasic methods. And as I mentioned, this is preferable way to keep this maze on beginning and basically get the structure to refine against your powder, because this is the best golden standard in research to get the structure out of your material. But as I mentioned, Chrysalis Pro is the very comprehensive program, and it has the whole automated or guided system, which allows you to work in the real space, on reciprocal space, have all necessary tools, like lots of automation. So if you are crystallographers, you will find a very powerful tools inside the software. If you are chemists that just want to get the structure, is basically click and you will get to the place where you can just build your model inside the software. Everything is contained and there is nice workflow that you can use to just solve a structure, even if you are not a professional crystallographer. So example, if we don't have a powder, so basically we still have a powder, that's a powder batch. Use one of the example of also Maciej MOFs that Maciej measured here. He actually activated the MOF, so he basically hit it for extended period to get rid of all the solvent from inside, which very often results that the single crystals are not single crystals anymore, or they are very small. So on the size, you can see this is the size of the crystal on the mount. So basically, it's all dimensions are less than 20 microns, and the measurements on the modern instruments takes a day, unless you have a Rigaku high brilliancy rotating anode sources, then it's a factor of 10, so basically 2 hours. And if you have a proper full resolution data set, you can do more advanced structure analysis than just seeing the structure. For example, here, you want to check how good was the activation. So we basically, when we generated what is called differential maps, so saying what the model describes and what's inside the crystal, we see some leftovers, these green blobs of topology of electron density. And we were wondering, is this still our DMF solvent or something else, maybe water or something like that. So we use what is called a solvent mask, which allows you to calculate, and we prove that basically this is just nothing, and the MOF is fully activated. But yes, it's now you should remember that very small crystals that barely visible under a microscope can be used for single crystal analysis.
So as I mentioned earlier, coupled triazolate shows reversible phase transition, and this behavior we can test using other system. For example, for high temperature measurements, we use SmartLab SE diffractometer, automated multi-purpose X-ray diffractometer. This is fluor standing system with the options like automatic component recognition, automatic alignment. Here we can install 2 types of detectors. 1D detector detects Ultra 250, which is bigger than this one detects Ultra 2 on the Miniflex benchtop system, as well 2D detector EXPA 400 ER. We can also use here different types of beams, divergent beam, convergent beam, and parallel beam. It's possible to install on the fluor standing system different types of sample changers for high capacity, pre-aligned capillary, and as well, for example, 96 well plate for reflection and transmission geometry. And for non-ambient measurements, we have, for example, from Rigaku, special attachments like Reactor X, multi-purpose high-temperature attachment, or XRD DSC attachment. As well, we can also install the attachments from Anton Parr. I'd like to focus your attention on the Reactor X. Here we can heat the sample from room temperature to 1000 degrees with the maximum speed 300 degrees per minute. The sample is heated by the IR radiation from the bottom, and it's possible to use here, of course, inert gas, humid gas, but also corrosive gases like even hydrogen up to 75% volume, and then we can heat to 1000 degrees the sample. And copper triazolate, when it's heated to higher temperature, higher than 120 degrees, shows phase transition from tetragonal crystal system to cubic crystal system, and subsequently cooling the sample leads to again to the tetragonal phase. If we check the distances between the copper ions and nitrogen atoms, we can consider 2 different copper ions in the structure. Here is the structure unit of low temperature phase. We can consider two types of distorted octahedra. One is a flattened one, marked here with a green color, and the second one is elongated one, marked with a red color. At higher temperature, this distortion disappears, and we observe the equal bond lengths between copper atom and nitrogen atoms, as well. If we consider, for example, non-bonding copper ions, the distance is here in this high temperature phase equal.
So what happens if the phase transition is more complicated than we shown here? Sometimes the change is so drastic in your MOF that you are stuck and you cannot solve the crystal structure for powder. So you basically can prepare your powder, open the reactor, take the leftover powder and go to electron diffraction. We will talk, and I will introduce the instrument slightly later, but I just want to show you here that you have an option to use attachment or sample holder from Hummingbird Scientific with the MEMS heating chips, which allows you to heat the sample in a similar range. And on the same grain or crystal, this is less than 1 micron crystal, you can get exactly the same structures. So if you cannot solve your phase transition from powder, like you cannot save your crystal structure from powder after phase transition, you can still go to Rigaku electron diffraction, and without recrystallization, changing anything in your phase, in your powder, risking any changes, actually continue your measurements with Rigaku instruments. So Synergy platform have its own attachment. Some of them, they are possible also for the smart lab, but most of them are designed to be open flow cryostats, because in the most cases we want to lower the temperature, which means that they are more popular cryostats than the heaters. Although we do provide hot gas blowers. For example, XDS hot blower, which goes to 1000, 2000 kelvins. But in most cases, we will work in a low temperature. This open flow design allows you to integrate your changes, variable temperature, integrate them with the other non-ambient sample conditions. For example, now very popular laser and light emitting diodes sample environment, which allows you to do time resolved or pump probe experiments, including the variable temperature with it. You can include a small called mini DAC, which can be cooled down. So you can do variable temperature change when the sample is under extreme pressures. Or just use both powders and single crystal measurements at very high pressure. This is 120 DAC, which allows you have a very large opening for your crystals, so 120 degrees, which allows you to access sample and collect very complete data. It's also compatible with the Synergy systems. So usually you see that I'm presenting you a rotating anode, so platform R system, because they provide much more intensity, allowing the very quick measurements. So I took the same powder that we already discussed, copper MOF, and I checked what's happening in the low temperature. And as was designed for the MOF and expected, we don't expect any more changes. We do see some small changes on the primary peaks, which is consistent with sample being slowly frozen and crystal getting more consistent in the build. As you can see, each of the steps of the rotating anode instrument can be just 20 seconds per scan per temperature. It's because the single crystal instruments using extremely large detectors. So as you can see, we collect data from almost complete Debye rings. So we have advantages of the area detector, because this is how detectors instruments are built. Here in the corner, you can see how the data collection is quickly do and how we use the Hall detector. It's a small amount of the sample closed in a Kapton tube that will just spin and collect data. So as I mentioned, 23 seconds per scan is not bad, but Maciej has another instrument to show you.
Another example of variable temperature measurements is a case of iron triazolate. This compound is interesting due to his electrical conductivity as well wide hysteresis, high temperature spin crossover. For data collection, in this case, we use a high-end SmartLab diffractometer, which can be equipped with rotating anode. Rotating anode has high power 9 kV. Here we have a generator 9 kV. And rotating anode provides 5 times higher intensity in comparison to the standard seal tube. Also, on the SmartLab, we can install Johansson monochrommeter on the incident side, where we can generate pure K alpha 1 powder pattern. Three different detectors can we install on the SmartLab diffractometer for data collection. I use the 2D HiPix 3000 detector with large detector window. The data were collected using XRD DSC attachment, which enables simultaneous measurement of XRD and DSC signal, where the sample is mounted on the right-hand side, and here on the left-hand side we have reference sample. Sample amount is between 310 milligram, and we can cool the sample to -40 and heat to maximum 350 degrees. We can perform the measurements under air, under inert gas, humid gas atmosphere. From the software point of view, we have the option to set up measurement conditions by using XRD DSC measurement, that on the right-hand side, we can specify the conditions for DSC measurement, and on the right-hand side, we can specify the measurement conditions for XRD. And during the data collection in display area, you can observe simultaneously both XRD pattern as well the results from DSC measurement. The iron triazolate shows reversible phase transition. During the heating the sample, we observe endothermic effect, and this endothermic effect is connected with the phase transition between low temperature and high temperature phase. This phase transition, here we observe phase transition is occurring in the same crystal system and space group, but we observe elongation of the unit cell parameter, as well increase of the volume of the unit cell, as well we observe spin crossover in this case. We collected the data here within 540 degree to theta. The sample was heated to the maximum 340 degree.
So what happened here is that this particle material was very hard to get objects any larger than usually, which is very good for the powder measurements, which is what actually you want to do. You want to have a very small unified powder data. Also, application of the calorimetry very often destroys the samples to the level that there is no way to get larger samples. And if you have a new phase that you cannot recrystallize or touch material, you are stuck and you sometimes cannot solve the structure. So then the electron diffraction comes to the rescue when we can break this 1 micron barrier and explore the crystal structures using the electrons rather than X-rays. So this is an example of this thiazole iron MOF. And I was able to solve it from just one grain of the size of basically nanometers. The whole data collection was 5 minutes and 30 seconds. And basically, the whole analysis is like 1 hour or something like that. And it was in very good agreement with solution that Maciej obtained from the powder data, but it allows us to understand all the basic changes that are happening during the phase transition. So as I took the picture, I tried to do it with X-rays, but as you can see, the powder from here was really, really fine, and there was no option to do it with X-rays. So we have a new instrument, which is called Crystal Lab Synergy D. It's still part of the Synergy platform, but as you can see, it looks completely different and not typical X-ray diffractometers, because inside we have a beamline delivered by GOL, our partner, which built us a beamline for electron diffraction. And we're using our own design and the best detectors, HiPix direct photo counting detectors. And as I mentioned, we will use Chris Alice Pro because it's a Synergy platform. So we have the same easy to use and automated workflows that you know from the X-ray instruments. Of course, there is a goniometer because it's a diffractometer. And we have a bunch of different attachments and sample conditions, which is perfect for MOF research because 3D is not just a crystal structure, allows you to do similar like with all other diffractometers, variable temperature experiments because of the control like a gas cell heating holder, which you can see here. You can do the gas exchange experiments and measure in situ in the liquid, so crystallization or liquid exchange in your framework. And we can provide a basic, because the sample is in a vacuum and a small amount, we can provide a basic elemental analysis using the EDS system that is also integrated inside the diffractometer. So this instrument is driven porous material research in extremes. We have a bunch of very active users which are using Synergy D to put a very big step forward in all material research, advanced fields. And as you can see, there is this gas absorption and separation, but also not only MOFs, but also COFSIFs and all the next generation material that are based on MOF knowledge that you developed. So here's an example of follow-up on that research. You find the reference on the bottom. The authors, the chemists, want to prove that they can lock the framework for changing phase transition. So let's say that they want to control the phase transition, they change the design of the material. To do this, they came up with the clever idea to change the linker to being more stiff, provide more stiffness to the framework itself. So they grow the linker and they provide the materials, and indeed they lock in transition. But to fully understand this, they need to actually have a understanding how the structure changed during the phase transition, and this was done with the 3D on simple grain, less than 1 microns. After that, the full analysis of the powder was done, and we could easily find evidence that the middle one still provide change in volume with the temperature, but it's not enough to provide the phase transition like it happened in the basic version. And then when they exchange to the CTR ligand, the stiffness of the framework is so big that it doesn't show any changes in the volume or the unit cell, and they completely eliminated the phase transition.
So the next example of MOFs, MFO4 bromide. In this case, we combine two different techniques, powder diffraction and electron diffraction. In this research, the goal was to investigate how the pore aperture has influence on the krypton-xenon uptake, retention, and release. In it was confirmed that in case of bromide phase, xenon was stable at ambient conditions, and 68% of xenon retained in NFO4 bromide after 42 days. This MOF consists of benzo-bis triazolate ligands, and here you can also see SBU of this MOF, which contains two types of zinc. One is octahedrally coordinated, and the next is tetrahedrally coordinated. And here on the right-hand side, you can see the unit cell with the pore aperture, and here are the halides ligands. In case of bromide, this diameter of the pore is smaller than in case of chloride. In this case, MFO4 as well bromide and chloride crystallize in shape of very small submicrons crystals, and it was not possible to use such a crystal for single crystal analysis. And in this case, electron diffraction was applied for data collection.
Yes, and again, I saved you a picture of the grain I selected to solve the structure. So you can see a picture of the solved structure, and here are the parameters that we later use for further analysis. And as you can see, the grain is, you can see the slightly larger cubes, there's leftovers, but the small grain, basically less than the diagonal here is, it's only less than half microns, and just gives you how quick this analysis can be. So as I mentioned, it's just 2 minutes per grain. You measure several grains usually just to have a better statistic. So the whole analysis is 30 minutes, and the sample preparation is 10 minutes. We have lots of documentation on it if you want to learn more about it, to understand better how you use electron diffraction and how you collect data. But generally, it's very easy and available technique already using electron diffractometer and not a dedicated microscope for electron diffraction.
Yes, exactly. And the crystal model, which Jakub obtained after the analysis of the data from electron diffraction, I used later for Rietveld refinement to check the bulk sample. And also to check to prove the purity of the compound. In such a case, I collected the data on the SmartLab diffractometer equipped with rotating anode, also with the high temperature chamber from Anton Park HTK 1200. Prior to the measurement, I evacuated the sample 4.5 hours at 120 degrees to remove all occluded solvent molecules in the pores. And after that, I collected the data within 1.5 hours. And then I performed the Rietveld refinement. Here you can see the refined parameters, Rietveld refinement plot, as well the residual plot here at the bottom. And RWP in this case was below 9%. We also proved that the obtained unit cell parameters from different methods, like from electron diffraction and also from powder data, were very, very similar. Another application of XRD methods are now in many laboratories for automation, especially for example automatic synthesis. There are special robots. They can prepare the samples, and after that the samples are prepared for the well plate. Here we have 96 position. We can perform the measurements in reflection as well in transmission measurements. When, for example, the sample was filtrated from the solvent by combination with the cluster analysis in the software, we can analyze huge data sets. At the same time, we can group the powder patterns based on the similarity, and as well, we can perform quantitative phase analysis. Rigaku developed special method, which is called direct derivation method. This is patented method for quantitative phase analysis in case we don't have crystal model. Like you know, probably for Rietveld refinement, if we want to use Rietveld analysis for a quantitative phase analysis, we need always to have crystal model, but sometimes we have unknown compounds, unknown phases, and this type of analysis is not possible. In such a case, we apply direct derivation method for crystalline, for amorphous phases, and based on the measured powder pattern for the single phase and information about composition of the phase, we can perform a quantitative phase analysis.
Okay, so as Maciej mentioned, we do have a method that allows you to do the analysis without knowing all the phases, just using intensities. But if you want to do it Rietveld, you need to know all the phases. And what happens if your powder pattern has something that it's not in database and it's not something that is in the chemist notes, and you completely lost. So you go back to electron diffraction as we extended our cluster analysis and batch processing to the electron diffraction. We do also support the plates in transmission mode on the single crystal instrument, but it's similar like to SmartLab, but with electron diffraction, you can do what we say grain by grain, or sometimes as I call it, missing phase or polymorph search, because it can go automatic phase by phase with completely unattended measurements, find the grains, center and measure it, and combine it everything. So this is the slide showing you application for actually with the medicine. So you have active pharmaceutical ingredients and some filler. This filler, of course, could be a MOF, not a sugar. It's just an example. But in the say that our software do support cluster analysis, crystalline straw, have a smart data management plugin, and a bulk analysis, which allows you to automatically find and group all the phases and get the solution of the crystal structure for all the phases that you have in your own in your sample.
So to conclude our presentation, Rigaku's diffraction instrumentation enables ab initio structure solution from powder data, from single crystal data, as well from electron diffraction. We can solve the data from samples like powders, microcrystal cluster, individual grains. We can investigate dynamic MOF behavior, performing measurements in situ, non-ambient. Also, we can perform in measurements or studies like gas-induced structural changes. We can observe simultaneous structural and thermal analysis. And as well, we can also offer here full automation and high throughput for MOF synthesis. At the end, we would like to thank Professor Dirk Vollmer and his group from Augsburg University, as well Professor Hanna Bunsen from Magdeburg University, for providing the samples and also for the good collaboration with us. And at the end, we want to thank you also for your kind attention.
Okay, thank you very much for this nice lecture, for the introduction of your equipment and its capabilities for MOF research. I'm sure that this lecture will be helpful and interesting for MOF researchers. So now we have time for questions, and if you have questions, you can raise your hand, unmute yourself, or you can chat. You can write the question in the chat, please. It looks like our participants are impressed.
You can always leave comments under YouTube video, and we try to follow up there, or just contact us directly.
All right.
Yes, for sure. And we will also publish the recording on social media, so you can comment there and reach the speakers with your questions. Okay, we have a question, yes, in the chat. So how important is the initial crystallization quality to get the best results with the Rigaku diffraction instruments? And is the thermal degradation of the compound a concern?
Maciej, this is something for you, but I can also...
Yes, it's for Dr. Grzywa from Nico to Philly. Sorry if I pronounce not correctly your surname.
One moment.
I think it's a question of the quality of the powder.
Of course, the powder quality is quite important. For example, for structure solution from powder data, very often it's important to have pure phase, or at least we know what kind of impurities are inside. Then the first step is quite difficult in powder diffraction to obtain the unit cell parameters indexing. And for indexing, we need to know information about which peaks belongs to the phase we want to solve from the data. If you have some impurities or small amount of amorphous phase, this will not affect the process of the analysis. But yeah, we need to know at least which peaks in the powder pattern. It means the best is to have pure phase compound. If it's what I mentioned, if a small amount of the amorphous phase, this will not affect the analysis.
So I want to comment on the second part of the question about the thermal degradation.
Yes, please.
There are both that survive activation. There are the one that doesn't survive. This is where I showed those cryostat, open flow cryostats are getting useful. So even if you cannot find a single crystal and you don't have access to electron diffraction, you can try to collect powder data on single crystal instruments in low temperature, usually freezing sample to 100 K, which we do regularly for both X-ray measurements and electron diffraction measurements, helps the sample, protects the sample from losing the solvent and losing the diffraction power. Because if you're talking about the porous material, very often the extended measurements, extended time being in the beam or on a dry air, which is sometimes required, or dry nitrogen to protect it from basically damage from the radiation itself, will also destroy your MOF. So freezing the sample is possible. Also possible, it was not shown here, but it's also possible on the powder instruments from Rigaku. But it's more popular to have these attachments on the single crystal instruments. But the other thing is that also SCXRD as a dedicated diffractometer, not TEM, has a very low dose, and it's designed to operate at very low dose and not destroy the crystals. So if you, for example, had experience already with the microscopes, with the TEMs, and you always observe that your material is decomposing or getting crystallinity inside it, it's usually not the case on the dedicated diffractometers, which use a very low dose of electron beam to provide only diffraction, not imaging. So both of those things can be adapted. And if you are stuck with the powder solution because your powder is not good enough, you can always go, as you show you, to the single crystal instrument and try to collect what is this from the batch of your powder, or go to Electron and go grain by grain to identify all the phases in your powder sample.
Thank you for such a detailed answer. Okay, yes, and in the chat, Nika wrote, thank you both. That's great to know. What are the biggest challenge when scaling up MOF production, and how does your technology help there?
If you don't mind, I can answer. So basically, the high throughput methods. So scaling up production will mean that you will have to test multiple conditions for synthesis, for modification on your MOF, and you will end up with the hundreds of samples that you want to measure. And then if you're using cheap metal, it's usually not a problem. You will get in the problems when you start using more expensive metals, and your supervisor or owner of the company will say that, oh, we are not buying another kilo of this gold for you. Then going to the micro powder diffraction on electron diffractions or small amount of the samples is the way to go to screen the conditions the best for deciding to sell your product to industry. And this is where the automation going through, when you can measure basically hundreds of thousands of samples fully automated in our instruments.
Okay, thank you. Some more questions. Okay, I don't see questions in the chat, and I don't see raised hands. So I would like to thank again for accepting our invitation and for being with us today. Thank you very much for this inspiring talk. It's, I repeat once more, it's quite useful for MOF researchers. Have a nice evening, and yes, see you in the next webinar.